Half a day students, we're going to be going over radical expressions. The first thing you need to memorize and to know are the perfect squares and their square roots. So we're going to do this first by squaring the numbers from 1 to 12. For example, 1 times 1 is 1, 2 times 2 is 4. Then we have 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. So when we have something like this, if I said 7 squared is equal to 49, this just tells me that the square root of 49 is 7. Now that we know the perfect squares and their square roots, we can go into some of the properties of radicals. Right now we're actually going to concentrate on this first and third ones. So looking at this first one, we say that the square root of a squared is equal to the square root of a squared is equal to a. Basically, this just tells us that the square root and the square, they cancel each other out, right? So the square root of 10 squared is just 10. In the same way, if I was to have square root of 10 squared, that would also be 10. This and this cancel each other out. In the same way, when you have a square root multiplied by itself, you'll have square root of a times square root of a. It'll just be the number. So if I was to have square root of 5 times the square root of 5, this would just be equal to 5. Now we'll go into the multiplication of radicals. So whenever you're multiplying, if you have radical times a radical, you can actually combine that into one square root and they're multiplied in the inside. So looking at this, square root of 8 times square root of 2, I can combine this underneath the one radical to be 8 times 2. From there, square root of 8 times 2 is going to be 16. And then I know that the square root of 16 is a perfect square. Its square root is 4. Once I take the square root, I no longer need to put this symbol. And this next one, I'll do the same thing. The square root of 50 times 2. That's equal to 100, right? The square root of 100 is 10. This is what we said over here. We said that a square root multiplied to itself, it's just equal to the number inside. So square root of 5 times square root of 5 is just equal to 5. Or you could have put square root of 25, and square root of 25 is just 5. So either way, it doesn't matter. And in the next slide, we're actually going to be looking at, okay, so if I can see that the square root of a times the square root of b is equal to square root of ab, it makes sense if I also was to start with square root of ab, that I can split it up to square root of a times square root of b. We're going to do that in the next one when we're simplifying numbers within square roots that are not perfect squares. So we'll look at square root of 20. What you want to do when you're simplifying square roots with non-perfect squares inside them, you want to break it up into its factors, and you want one of the factors to be a perfect square. So for something like this, I might actually just list my perfect squares on the side. Okay, I have 4, 9, 16, 25, 36, 49, 64, 81, 100. And from there, I can just look at them easily instead of having to keep on thinking about it. So I'll look at 20. 20 is divisible by 4, right? So I can break this up into square root of 4 times square root of 5, right? Because 20 is just 4 times 5. So I can split up into two different radicals. From there, okay, I know the square root of 4 is 2. Square root of 5, you want to look at it again, just to make sure you didn't miss anything. Is 5 divisible by any of these perfect squares listed over here? It's not, so I'm actually just going to leave it, and this is the simplest form. We'll try again for this one. Square root of 54. So 54 I know is equal to 9 times 6. So I'll say, okay, this is the same as 9 times 6. I'll split this up into two different radicals. Square root of 9 times square root of 6. I know the square root of 9 is 3. No more square root sign, right? Square root of 6. 6 is not divisible by any of the perfect squares. So I'll just leave it as like that. 125. This is actually divisible by 25. So this is 25 times 5. From there, break it up. The square root of 25 is 5. Then 5 I cannot simplify further, so I'm going to leave that as square root of 5. And that's it simplified. Square root of 72. Okay, I know this is also divisible by 9, so I could say this is 9 times 8. Okay, so a square root of 9 times square root of 8. So I have 3 square root of 8. You always want to look back again to see if it's divisible by anything else. So looking at this 8, I know that 8 is divisible by 4, right? So I can actually break this one up one step further. So I can say, okay, this is equivalent to 3 times square root of 4 times square root of 2. Square root of 4 I know is 2, so we have 3 times 2 square root 2. From there, I'll just multiply 3 and 2 to get 6 square root 2. So basically, the issue here is that when I did 72, I jumped straight to knowing, okay, it's divisible by 9. However, it's also divisible by a bigger perfect square, which is 36. And I'll actually show you, okay, this solved using 36 on the side, just really small here. Okay, so 72 is also equal to square root of 36 times square root of 2. From there, square root of 36 is 6 square root 2. So it doesn't matter which perfect square you use. So if you use a smaller one instead, you can actually just continue to break it down. It's just more steps. So if you make a mistake, if you're not sure, you could use a smaller perfect square. But obviously using the bigger one is going to be easier. Fewer steps. So when we're simplifying square roots with variables, we're actually going to bring back to mind what exponents really are. So if I was to have the square root of x raised to 4, this just means the square root of x times x times x times x, right? And when you're taking the square root, and for square roots, if you have two of the same variable or the same number in the inside, it's worth 2 on the outside. Basically, just because this is just x squared, right? X times x is x squared. This is x squared. This is the same as square root of x times square root of x squared times square root of x squared, which is just going to become x times x, right? Which is x squared. So if you break it up like that, it really just tells us that 2 of each of these, right, is just equivalent to, let me just highlight one of them. So this is the same as this, right? Becomes that by itself, which is 1x on the outside. We can also see this when we work with numbers, right? So if I was to have square root of 7 times 7, that would just be 7, right? Because 7 times 7 is 49, and I know the square root of 49 is 7. So whenever you have two factors inside that are the exact same, you can actually take it out and as one factor on the outside. Looking now at a raised to 8, since it's raised to an even number, I'll have a bunch of pairs of a's in there, right? Like just like how we had this x, x, and x and x. I'll have a bunch of pairs. So if this was made up of different pairs, I would just divide it by 2, right? So this is just becoming a to the 4th. You can test it. You can say, okay, what's a to the 4th squared, right? I already know that I multiply this, so that'll just be a to the 8th. If you're not sure, you can just apply the square and then find out from there if it's true. If we have an odd exponent, x raised to 7, obviously I can't take out pairs from 7. So what I'm going to do is I'm going to split it up into an even that I can take out, remove, and then one odd. So basically we're dividing it into a perfect square and a non-perfect square, just like we did with the numbers. So we have x raised to 6 times x raised to 1, right? I'll split that up. Okay, I'll say, okay, x raised to 6 times square root of x. The square root of x raised to 6 is going to be x raised to 3 times square root of x. Looking at this one, 18 x raised to 4 within a radical. I'll break up the number and break up the exponent, the variable. So we have square root of 9 times 2. Then we have x raised to 4. I don't need to break that up because it's already an even exponent. Square root of 9, I know it's going to be 3. Square root of x to the 4th is going to be x squared. I do have this 2 that I cannot take out of the radical, so I'm going to leave it inside. I'm left with that. This one here, okay, I'll have to break up any of the odd ones. X cubed is going to be x squared times x. Y to the 10th, I don't need to split that up. Z to the 15th is going to be z to the 7th times, z to the 14th times z. From there, I'll take out any of my perfect squares, which are my variables with even exponents. So we have x squared. We're going to divide that exponent to be x. Y to the 10 becomes y to the 5th on the outside. Z to the 14th becomes z to the 7th. Inside the radical, I have x and z. Moving on to another property of radicals, we're looking now at division. So in the same way that we could break up a factor into two different radicals, we can do the same for a ratio. So if I have a square root of a over b, we can break it up into square root of a over square root of b. So we'll try for this one, square root of 4 over 36. If the numbers in the inside are divisible, I suggest simplifying the inside first and then taking the square root. Otherwise, we'll just break it up. So 4 is not, I cannot divide 4 by 36, so I'll just say, okay, square root of 4 over square root of 36. And the square root of 4 is 2. Square root of 36 is 6. From there, I can simplify this. 2 over 6 is equal to 1 over 3. Looking at this next one, 144 over 25. 25 cannot go into 144 equally, so I'm actually just going to do square root of 144 over square root of 25. That's equal to 12 over, not 25, but 5. I cannot simplify that, so that's complete. So for these problems, we were lucky because in our denominators, we had perfect squares. So one of the rules for math is that you cannot have a radical in the denominator. So we're going to look at some examples next that have non-perfect squares in the denominator, and we're going to do what we call rationalizing the denominator. So looking at this first one, we're going to do the same thing at first, breaking it up into two different radicals. So we have square root of 2 divided by square root of 7. You'll want to simplify each of them first. If they're not simplified, these two are both simplified, meaning that neither of the numbers inside are divisible by any perfect squares. So what you're going to do is called rationalizing the denominator. So since we don't want a radical in our denominator, in order to get rid of it, we're actually going to multiply it by both sides by the denominator. So multiply by that radical, that's square root of 7. When we do this, square root of 2 times square root of 7, I know that's going to become square root of 14, because I'm multiplying those two together. From the bottom, square root of 7 times square root of 7, that's just the square root of 49, but I also know that any square root multiplied to itself is going to be equal to just the number in the inside. So this becomes square root of 14 over 7. And if you can simplify that numerator, square root of 14, is 14 divisible by any perfect squares? No, only 1, right? So I cannot divide it by 4, obviously cannot divide it by 9, so this is actually simplified. So doing this one now, we'll split this up in the bottom. Square root of 2 divided by square root of 12. This I can actually simplify, so I have, okay, square root of 2 over, this is 3 times 4, so this will become square root of 4, square root of 3, square root of 2 over 2 square root 3. We want to multiply this. When we're multiplying by 2 square root 3 divided by 2 square root 3. We're actually going to multiply this, so we have a number in the front. So we have 2. Square root of 2 times square root of 3 is square root of 6. Divided by, this will become 4 times square root of 3 times square root of 3 is 3. So we have 2 square root 6 over 12. We'll have to take it one step further. 2 and 12, they're both divisible by 2, so this becomes square root 6 over 6. Now we're going to look into some other operations on radicals or involving radicals. So when you are adding or subtracting radicals with the same number in the inside, so the same radical, right, the same square root, you actually just treat it like it's a variable. So if I had x plus x, that's just equal to 2x. So square root of 5 plus square root of 5, this is just equal to 2 square root of 5. The same way 6 root 3 plus 2 root 3, this is just 6 plus 2 is 8 root 3. Treat it like a variable. When you see something like this, okay, 20, 45, 125, what you'll actually want to do is simplify each of them, and then you should be able to simplify from there. Combine them from there. So we have square root of 20. 20 is just 4 times 5, so we have square root of 4, square root of 5, plus 45, that's divisible by 9, so we have square root of 9, square root of 5, minus 125, which is divisible by 25, so we have square root of 25, square root of 5. Simplify it, so we have square root of 4 is 2, plus square root of 9 becomes 3 root 5, 25 becomes 5 root 5. So from here we have 2 root 5 plus 3 root 5. That's going to be 5 root 5 minus 5 root 5. This is going to become 0. So this whole thing actually equals to 0. Looking at this last one, so now we actually have numbers in front. So we'll just have to go that one extra step to multiply the numbers also. It's the same thing. So this is going to become 2 root 5, right? We said square root of 20 is 2 root 5. So we have 2 times 2 square root of 5 plus 4 times square root of 45, we said was 3 root 5 minus 2 times 5 root 5. Now I'll simplify it. 2 times 2, we'll say it's okay. So we have 4 square root of 5. 4 times 3 becomes 12. Plus 12 square root of 5 minus 10 square root of 5. 4 plus 12 becomes 16. Minus 10 is 6 square root of 5. So a good rule of thumb for this is you multiply the numbers that are outside together. See, so we have numbers that are outside the radical. So we have 4, 2 and 2, so we multiply that to become 4, right? 4 and 3 multiply become 12. You can multiply numbers that are both outside the radical or both inside the radical. So in the same way, okay, I had square root of 4 times square root of 5 is the same as square root of 4 times 5. So multiply either both the outside or both the inside. That's going to come into play a lot here. So we're actually going to use old stuff. Now we're combining things we've learned before. So we're going to distribute this square root of 5 to here. So square root of 5 times 3. Again, numbers have to be either both inside or both outside. So one is inside, one is outside. I'm just going to say, okay, this is just like 3 times a, right? It's going to be 3a. So we have 3 square root of 5 minus 2 square root of 5 times square root of 5. So we do both inside or both outside. We have two numbers on the inside. We know that square root of 5 times square root of 5 is just equal to 5. So I can just jump to 3 square root of 5 minus 2 times 5, which is going to give us 3 root 5 minus 10. For this next one, I'm distributing now square root of x. So we have 4 square root of x minus 2 square root of x times square root of x. In the same way, works in the same way, so we have 4 root x minus 2 times square root of x times square root of x is just going to be x. you can just leave it like this. For this next one, we have a pair of binomials multiplied together. If you remember, we have to FOIL it, so we're going to FOIL. First, square root 3 times square root 3, that's just going to be 3. Outside, minus 2 times square root 3. Inside, plus 1 root 3, or just square root 3. Last becomes minus 2. From there, we combine our like terms. In this one, okay, I know I have two things that have square root 3. So let's say, okay, negative 2 square root 3 plus 1 square root 3 is just going to be negative root 3. And then 3 minus 2 is just 1. And you can put it either as 1 minus root 3 or negative root 3 plus 1. Both will be accepted. Now we're going to go into rationalizing the denominator using the conjugate. So the conjugate is a term that we use in math. We're going to go over what it is. But first of all, to rationalize the denominator containing two terms with one or more square roots, so we have square root here, right? Since we don't want square roots in the denominator, what we have to do is multiply the numerator and the denominator by the conjugate. So the conjugate of something is going to be basically the same two terms, but I'm going to change the middle operation. So the conjugate of 3 minus root 5 is going to be 3 plus root 5. And this, we choose this because when I FOIL it, the middle terms are going to cancel each other out, and those are the terms that are going to have the radicals in it. So looking at this first one, the conjugate of 4 minus root 2 is going to be 4 plus root 2, right? So multiply each of these by 4 plus root 2. Okay, so 5 times 4 plus root 2 is going to be 20 plus 5 square root 2. I just did that by distributing. For this next one, we'll FOIL. So we have first 4 times 4, 16, outside, plus 4 root 2, inside, minus 4 root 2. Last is going to be minus square root of 2 times square root of 2, which is just 2. From here, we'll just cancel what needs to be canceled or combine like terms. Positive 4 root 2 minus 4 root 2, those just cancel each other out, so I can say, okay, that's gone. And now that I have no radicals in my denominator, I can just simplify this and then be done. So 20 plus 5 square root 2 over 16 minus 2, which is 14. I cannot simplify this further. If this 5 was even, then I could. Otherwise, we're good. Let me just fix that 2 real fast. Okay, so now looking at this last one here, it also works if you have two different radicals. So we're going to multiply now by square root of 2 minus square root of 5. Okay, so 3 times root 2 minus 3 times root 5. Over FOIL again. First, square root of 2 times square root of 2 is 2. Minus root 5 root 2 plus root 5 root 2. Last. Root 5 times root 5 is 5. From there, okay, I can say again, wow, this happens to cancel each other out. Negative 5 root 2 plus 5 root 2. So now we can just simplify. So the numerator, I don't even need to combine. I'll just leave this as two different radicals because we cannot combine them actually. And then now we have 2 minus 5 is going to become negative 3. From there, since all of these numbers are divisible by 3, or have a coefficient of 3, so I'm going to just simplify this to be square root of 2 minus square root of 5 over negative 1. This just means negative square root 2 plus square root 5. I could have actually just divided each of these by negative 3. So 3 divided by negative 3 is negative 1. Negative 3 divided by negative 3 is positive 1. Some practice problems here. Square root of 20 times square root of 45. So neither of these are perfect squares. What you actually want to do is multiply them together and then break it down from there. So we can say square root of 20 times square root of 45. So I'll multiply this on the sides. We have 45 times 20. Zeros, we have 10. Carry the 1. We have 900. Underneath the square root. From there, okay, I can already see that this is actually a perfect square, but I don't know the perfect square is that big. But I know it's divisible by, since it ends in 0, 0, I know it's divisible by 100. So this is actually going to come out to square root of 9 times square root of 100. These are both perfect squares, which makes it nice. So square root of 9 is 3. Square root of 100 is 10. So we know that the square root of 900 is 30. Working now on this next one, I'm going to break it up. Since 108 does not go into 192, I'm going to break it up into two different ones. 192 divided by 108. And 192 is actually divisible by 64, so this is going to be square root of 64 times square root of 3. 108 is divisible by 36, square root of 3. So from there, I can already see square root of 3 over square root of 3. I can actually cancel those two out. Square root of 64 is 8. Square root of 36 is 6. I'll just simplify. 8 divided by 6. They're both divisible by 2, so that becomes 4 over 3. Looking at this last one, I'll actually just simplify each of them. So I'll split up the number by itself. So square root of 250. 250 is divisible by 25. So I can say, okay, this is 25 times 10. And then we have variables. Again, variables, if it's odd, we're going to actually split up into an even multiplied by an odd. So I'm going to break it up into x squared times x. And then y to the 8th, I'll just leave by itself since it's even. From there, I can break this down. I'm going to pull out my perfect squares. So we have, let me just do this. We have square root of 25. That's going to be equal to 5. This is a perfect square. This is a perfect square, so I can bring those out. So we have square root of 25 is 5. Square root of x squared is 2 divided by 2, which is 1. Y to the 8th is going to become y to the 4th because we're going to divide it by 2 also. So y to the 4th. Then what do I have left inside? I just have 10 and x. And that is simplified. For the last part of this pretty long lesson, we're going to look at solving radical equations. Again, whenever we're solving equations, we always do the opposite, right? In order to isolate our variable. If it's x plus 5, we'll subtract 5. If it's x multiplied by 2, we'll divide by 2. So we always do the opposite. If we have square root of x, the opposite of square root is square. So we're actually just going to square each of them. So we have this square both sides. Square root of x squared is just x, right? Equals to 49. Okay, this one will actually square both sides again. This gives us x is equal to square root and square cancel each other out, so we have 12. For this one, there'll be an extra step, so we'll square each side. So we have x plus 2 is equal to 100. Now solving for x, we'll subtract 2, subtract from each side. X is equal to 98. For this last one, actually, let's take a new page for the last one. Square root of 5x minus 6 is equal to x. I'll square both sides. That's 6, sorry. So we have 5x minus 6 is equal to x squared. So now we have a quadratic equation, which we know how to simplify, or to evaluate, I mean. We'll move everything to one side, wherever x squared is positive, and then solve by either factoring or using the quadratic equation. So I'll move everything to the right side. So we'll subtract 5x and add 6. So 0 is equal to x squared minus 5x plus 6. From there, we should be able to factor. Factors of 6 that give me a sum of 5 are 2 and 3, but we're going to make them negative. So this is equal to x minus 2 times x minus 3, which will give us x values of positive 2 and positive 3. That's it for this lesson. Please do the practice problems in your workbook, because this is actually not too hard of a lesson, but it does require a lot of practice, so good luck.